Welcome to Module 5 of Siemens Online Registered Installer Training, Optical Fiber Testing and Terminations. So like copper systems, optical fiber systems require proper testing to ensure that they're installing as intended and they're accurately characterized so that the transmission can be completed and there's no issues for the end user. Now, there are a number of considerations that we need to factor in when we think about overall performance of the cabling, which is affected by, primarily you're going to measure attenuation for these systems, which is the type of fiber that you're using, how long it is, the type of termination methods, which is going to impact, how many connectors you have in the channel, how many splices you have in the channel. But primarily, in addition to how it's installed and ensuring it's installed properly, the number one fault for all attenuation issues is almost exclusively dirty end faces. So cleanliness is the number one consideration for a properly operating optical fiber system. So, and of importance is that we're always trying to chase a performance level that one should be expected based upon the type of fiber that's used for your loss budget, but two is also within the loss budget for the applications that are intended to be used on the system. So we'll talk a little bit about the expected losses based upon the design as well as some of the system losses for common applications. As mentioned previously, the cleaning and inspection fiber is so critical to the overall system performance, as nearly all field issues are somehow attributable usually to the cleanliness of the end faces of the fiber. So if you want to have some success in installing fiber systems, you have to make sure you have the means to both inspect those end faces as well as have the proper cleaning tools to ensure that they're cleaned properly and inspected before being tested. So you can have fiber on the actual ferrules, the fiber themselves, the alignment sleeves, and even the dust caps. When something comes from the factory, even though it's been cleaned and polished, the dust caps over time can have an impact on that. Every time you remove a dust cap or something, or more importantly, every time you're about to mate a fiber into an adapter plate to mate with another fiber, you really need to inspect those end faces to make sure it's properly cleaned. Contaminants just come up time and time and time again. So inspecting those prior to testing, prior to mating, is very critical. And for example, cleaning an end face of a connector is one thing, but when you want to clean the end face of a connector that's behind an adapter plate, it's important to consider using cleaning sticks, which actually have the ability to clean both a regular fiber connector end face you might be holding in your hand, as well as clean the end face of a fiber that's already installed behind an adapter plate. So we're going to take a look now at calculating loss budgets, the loss budget to your system based upon the installed components. Now, the link attenuation allowance, or referred to more simply as the loss budget, is the sum of all the losses of the installed cabling, which is going to come into play to factor the cable attenuation itself, the attenuation of the optical fiber, the connector insertion loss that's introduced by connectorizing either end, and any splices inside also contributed to the insertion loss. Those added together determine your overall link attenuation. So while the connector terminations are kind of fixed numbers, and we'll cover that a little bit on the next slide, the cable attenuation for your link loss budget is actually a calculation that's made by determining the maximum cable attenuation of the fiber itself, which is defined in dBs per kilometers or decibels per kilometer, times the actual measured length in kilometers. And here on this slide, we've kind of listed what we covered from Module 4 in terms of what are the cable attenuations for the common multi-mode and single-mode fiber solutions. For the connector and splice insertion loss, well, the connector insertion loss is based on how many connectors that you have times the connector loss for each. Splice loss is same thing, the number of splices that are implemented within that link times the splice loss allowance. And the maximum allowances, if you don't know what the connector specifications are, the maximum allowances are 0.75 dB per connector and 0.3 dB per splice. And you can expect most manufacturers will have losses that are below those, but those are the maximum allowable. So if you set up the field tester for the default limits, that's what will allow you to achieve for field testing. So really the best way to explain this is to walk through an actual couple of examples. So we've got a couple of examples here. We'll start off with the simple one, which is calculating the link attenuation for 850 nanometers for a 100-meter 2-connector link with 2 splices using 50 125 micron laser optimized OM3 multimode fiber cable. So step 1 is going to be determine the cable attenuation. So in that case, OM3 multimode fiber cable has an attenuation of 3.0 dBs per kilometer, and you multiply that times 100 meters, which is 0.1 kilometers, and you get 0.3 dBs. The next step is to introduce your connector insertion loss. In this case, there's 2 mated connectors, so 2 times the TIA standard of 0.75 dBs equals 1.5 dB. Third, we're going to factor in the splice loss. Again, we see 2 splices here. 2 splices times the maximum TIA loss of 0.30 dBs is 0.60 dBs. So adding that all up, the total link attenuation is the attenuation of our cable, 0.3, plus our connectors, which is 1.5, plus our splices, which is 0.6, for a total of 2.40 dB. So when testing, you're going to want to ensure that your tested installed fiber cabling system is verified to be at less than 2.4 dBs to ensure proper installation. In some cases, I mentioned, if you have better splices or your connector losses are specified to be lower than that, you may find to be less than that. But this is a TIA kind of standards-based limit exercise. Now let's get a little bit more complex here. We'll do one with an MPO-based system, an array-based system. We'll do the same loss budget, so we'll do 850 nanometers for a 100-meter duplex array system using a 50 125 micron laser optimized OM4 multimode fiber cable. So we'll start with the cable performance, and as you remember, OM4 losses are the same as OM3, so it's 3.0 dBs per kilometer. We're doing 100 meters again, so 0.1 kilometers is 0.3 dBs. When we get to the connector insertion loss, because it's an MPO system that has plug-and-play modules at the end, we need to factor in both our MPO losses as well as our connector losses, like the LC connectors. So if they look at the table at the bottom, and these are included in all the spec sheets for plug-and-play modules, you see that the MPO loss for a OM4 system as well as an OM3 system is 0.4 dBs for the MPO connector, or the MTP connector I should say, and 0.25 for the LC connectors on the other side of the module. So in this case we have 2 MPO connectors at 0.4, we have 2 LC connectors at 0.25 for a total of 1.30 dBs. Next, we factor in, because we don't have any splices in this particular installation, the total link attenuation is simply the addition of the cable attenuation plus the connector insertion loss. So 0.30 dBs plus the 2 plug-and-play modules together combined for 1.30 dBs for a total loss of 1.60 dBs. In Module 1, we discussed the relationship between the TIA standards and the IEEE standards. And as a reminder, the IEEE standards are designed to cover the applications, primarily the Ethernet applications, both wired and wireless. But in this case, we're talking about not only wired connections, but optical fiber connections. And when they're doing their modeling, they base theirs on a 1.5 dB total connection and splice loss, which effectively means if you can have 2 TIA-compliant connectors in there at 0.75 dBs each for a total of 1.5, but if you want to introduce splice into there, you'll have to recover some loss from the connector styles that are implemented, and that's not always difficult. Your splices themselves might typically only be about 0.1 dB with a fusion splice, and connectors are typically going to be 0.5 dB or better. So not an issue, but it's good background to get an idea that these two groups do work together and what their understanding of the overall loss should be from the connector side. In terms of the cable side, they're in agreement with the TIA limits for the cables, so that's factored in as well. This table illustrates some of the loss budgets and supported distances of the IEEE Ethernet application, starting at gigabit Ethernet, which is 1000 base SX. And you'll note here that some of these applications are duplex, while some of them are based upon the MPO connector interfaces from end to end. So it's important to consider that. But what you'll see historically is that some of the lower speed, when I say lower speed, I'm kind of referring to gigabit and even 10 gigabit, were supported for pretty extended distances for both OM3 and OM4, and had some pretty healthy loss budgets for OM3 and OM4 as well, over 4 dBs for gigabit Ethernet, and over almost 3 dBs for 10 gig. What you see is as speeds have increased, those loss budgets have significantly reduced. So it's important to be aware not only of the loss budget of your installed cabling system, but ensure you're designing ideally cabling systems that will support some of these higher speed losses in the future so these applications be run. Again, the intent of a structured cabling system is to be in place for a minimum of 10 years. So if you have a customer right now that's running 10 gigabit, you can expect they'll be at 20, 25 or 40 gigabit at some point in the future. So it's important to be aware of those higher speeds and lower losses. So you really want to limit your lengths. Even though you can run gigabit out to 860 meters, that's not going to support 10 gigabit or 40 gigabit. So you really want to design systems ideally around OM4, which have that 100 meter supported distance. And if you can get losses less than 1.9 dB on your system, with the exception of 40G base SR4, which is an MPO system, then you're going to be in good shape moving forward all the way through. So when it comes to testing of the fiber cabling systems, you're going to be using an optical loss test set. That can range from a device that's specifically dedicated for fiber testing to a device that maybe is used for fiber and copper testing, but has different modules for both of those using a common platform. But historically, if we reference an optical loss test set, you're talking about two units. One is the light source, which actually transmits the light for testing, and the other is the power meter, which measures the power received at the system. And when you're doing these things, it's important to have an encircled flux compliant launch system. And most manufacturers are going to specify and state that they have that capability. If it's not built right into the tester, sometimes it's built into the launch cords. If not, in either situation, you have to introduce a mandrel situation where you actually have to buy some plastic mandrels and rotate the fiber around there for multiple turns, kind of specified to do it that way. And that's really just a way to ensure proper, consistent methods across the board. In either way, you need to engage and talk with the optical loss test set manufacturer to make sure you have the proper cords and launch conditions for doing that. Most importantly, you'll want to work with them to ensure that you're using their high quality reference grade test cords and not just standard jumpers. The high quality reference grade test cords are important because they have exceptionally good polishes and low losses to provide repeated testing. So they have some nice mechanical reliability, but even those cases, they're supposed to be replaced at somewhat regular intervals just because of the wear and tear of the mating and unmating of those connectors. Again, it's important to talk to your optical loss test set manufacturer and ensure you have the proper equipment for testing optical fiber systems. Now, the other type of test equipment that's out there is an optical time domain reflectometer, or OTDR for short. And these are much more higher end systems than a standard optical loss test set because they provide a little bit more about characterization of the fiber. So you don't just get a loss number, you actually see the loss events across the overall system. So it provides that trace of the fiber cable, and it gives you an idea from at distances where these events occurred and what those are along the way. They're a little bit more complex to operate, in fairness, than an optical loss test set, but if you're looking for characterization, it's absolutely essential. Some of the OTDRs may even have an optical loss test set capability built into them, but as a rule, you can't use those alone for measurement of loss testing. So let's kind of look at this as kind of a high level here. If you're looking at the two different types of testing tiers defined by TIA, you have tier 1, which is required, which is to use an optical loss test set and ensure that you've tested the link attenuation as well as evaluating the length and polarity. And most optical loss test sets have that. If not, you might have to just check the jacket labels themselves. And polarity is certainly something that can be visually verified. For tier 2, which is optional testing, is where you supplement that optical loss test set by introducing OTDR testing as well. And again, that provides characterization of the system of the installed fiber cabling. And the most important thing to consider for tier 2 is that you might have a loss. Maybe you have a loss budget of 1.5 dB and you test it and you come up at 1.4 and that looks great. The problem is that you could have one connector that's got exceptional loss over a dB and one that's performing very well that's 0.1, and you just don't realize that one of those connector terminations is bad or there's significant dirt on that end face. So characterization sometimes adds value. It's not required for all customers, but in many cases it may be required for a lot of outside plant or extended haul single mode systems like to do this because they can really more readily identify the loss events along the way. But for the purposes of warranty, only optical loss testing, tier 1 testing is required. Now, there are a few different fiber test reference methods, and some of them come into play depending on the configuration of the fiber system that you're testing. But for most systems, it's point A to point B with a couple connectors and adapters going between them. And for those, the one fiber or one cord reference method is recommended by TIA and IEC, which is International Electronic Committees, as well as Siemens. And in that case, the reason that's referenced is because a one cord reference method measures the loss of the fiber cable plus the two mated connections. So as you can see in the illustration here, the two cord reference method only captures the fiber cable plus one of the mated connections, and the three cord reference method only captures the fiber cable only. And again, there is a time and place for those, but they're usually for unique configurations of the fiber cabling system, or when you have situations where the fiber test equipment you have doesn't have the same interface as the fiber system that's undergoing test. So again, it's important to engage with your optical loss test set manufacturer to ensure you have the right configuration set up for cabling. But for all cases for warranty, you're looking at doing a one cord reference method, and we'll walk through the reference procedures. So walking through this, we see we have a power meter and we have our light source, and we have our test cord one, which is a test kind of a high quality reference grade test jumper. And we're going to record mate the two of those. We're going to make sure that the end faces are clean in all cases. We're going to connect the two of them together, record that optical power measurement P1, which is the reference power measurement. The second step is to disconnect that first test cord one from the power meter, not from the light source. Well, if you disconnect it from the light source, you have to start all over again. So you're disconnecting from the power meter, and then you're introducing test cord 2 to the power meter, and you're mating that to test cord 1 using a common adapter. For example, in this case, it'd be an LC adapter. Again, making sure you're inspecting the end faces of test cord 2 before you introduce it to the system. And then you're going to record that measured optical power and verify that it's within 0.1 dB from the measurement you made in the first step, P1. And that's important because that 0.1 dB ensures proper operation when you're using reference grade jumpers. Now, it's important to remember that in some cases the optical loss test sets have a reference button feature that skips this qualification step. So again, it's important to engage with your optical loss test set manufacturer and ensure their procedures match up, and they might have something that's a little bit simpler. Now, once you ensure you have that 0.1 dB of mating between your two test cords, you're going to disconnect them both from the adapter, and then you're connect test cord 1 to one of the cabling and test cord 2 to the other end and measure your optical loss. In this case, the loss of the link under test is going to be the measurement you just got, which is P2, and subtract P1, which is your original loss measurement, from that to determine your overall system loss. Now, TIA 568 .0-E defines this illustration here, which are the cabling system functional elements. And we're going to talk a little bit about those because we want to ensure that we know what type of fiber testing we should be doing for cabling subsystem 1 and cabling subsystems 2 and 3. For cabling subsystem 1, which is the red line shown in the illustration there, that's effectively your horizontal cabling when you're going from your distributor A or your telecommunication room to your equipment outlet. In the case of horizontal cabling, your link segments have to be tested in one direction and at one wavelength. I should say that's pretty much at least one direction and at least one wavelength. So that's all that's required for warranty. For multi-mode, that happens at 850 or 1300 nanometers. For single mode, that could be 1310 or 1550 nanometers. Some optical loss test sets will shoot both directions, both wavelengths just by default, so you may have that, but these are the minimum requirements for testing of cabling subsystem 1 or the horizontal cabling. So for cabling subsystems 2 and 3, which are the blue and green kind of dashed and dotted lines in the illustration, that's really your backbone cabling. That's going from your telecommunications room back to your MDF. It might be passing through an intermediate distributor. In these situations, the link segments must be tested in at least one direction at both wavelengths. So you're talking about, regardless of how your optical loss tests that are made default, you have to have a minimum of testing in one direction at, for example, 850 and 1300 for multi-mode and 1310 and 1550 for single mode. And like I said, some of this test equipment will automatically test in both wavelengths, which is actually better characterization, but testing in only one direction is required. Now, it's important to note that all the horizontal and backbone lengths have to be 100% tested for length, and that can be with your optical loss test set if it's supported. If you're using OTDR in Tier 2, you can introduce that, or in worst case, you can actually read the sequential measurements on the optical fiber jacket because you're really talking about usually installing one cable from point A to point B, so you have that easily visually identifiable. Now, for polarity and in some cases even troubleshooting, you might find yourself using what is referred to as a visual fault locator or VFL. Now, that's a light source that basically emits visible light, so you can actually see that visible light show up through the end of a connector, or you can actually usually see it through the jacket of a buffered or maybe lightly jacketed single or two fiber cable. In some cases, you can even see it through the connector housings along the way, so it's perfect for confirming polarity if you need to, but it's also great for identifying any issues in either the connectors or the cable from point A to point B. So now that we've covered optical fiber testing concepts, let's take a look at some of the actual optical fiber terminations that you'll be doing in the field for Siemens Solutions. First up is Siemens LightBow mechanical splice fiber connector. As we discussed earlier, this is something that's relatively easy to install for people. Doesn't require a high level of technician experience in this, just requires a good cleave of the fiber as it's done here. We have the video instructions as well as the detailed PDF instructions for these products.
The LightBow termination kit provides all the tools necessary to perform a successful fiber termination. Buffer stripper, jacket stripper, Kevlar scissors, precision rotary cleaver, electrical tape, termination tool, visual fault locator, marker, tweezers, strip template, and alcohol wipes. An included lanyard can also be used on the tool. The strip template card has both an SC side and an LC side. To begin, open the tool, select connector. In this case, it's an SC connector. Place into the SC pocket in the tool. Close the lid, press firmly until an audible click is heard, and then slip the lock collar forward. Place the boot on the 900 micron fiber and pull it back out of the way. Next, place the fiber on the strip template card. The first mark will be the reference dot at the back of the connector. The second will be the buffer strip length mark. A strip template is also located on the side of the termination tool, in the event strip template card is misplaced or unavailable. Both SC and LC lengths are represented. Using the 900 micron buffer strippers, remove 1/4 inch sections at a time to avoid breaking the fiber. Using the provided alcohol wipe, clean the fiber to remove any debris. Next, we are ready to use the rotary precision cleaver. Take the prepared fiber and place it into the 900 micron guide slot, the larger of the two. The end of the buffer should be placed at the 10 mm mark on the cleaver. Using your finger to hold the fiber in place, close the debris cover and the main cover of the cleaver. The fiber is now immobilized in the cleaver. Press down on the main cover to activate the cleaver. After the cleave process is complete, open the main cover. Place the cleaved fiber into the SC guide slot in the LightBow termination tool. Please note that both SC and LC positions are located in the tool. Gently slide the fiber forward into the back of the connector. The fiber reference mark will be at the back of the connector, and a slight tension bow will maintain pressure as the cover is opened. The connector can now be removed. After the connector has been terminated, use the 0.5 milliwatt VFL to verify the validity of the termination. Remove the dust cap and place the end face of the SC connector as shown into the end of the VFL. After turning the VFL on, observe the VFL window located closest to the end face of the connector for a bright red glowing light. If no light or a very faint glow is detected, the termination is good and the dust cap can be put back into place. When performing an LC termination, it will be necessary to use the LC adapter in the VFL. Place the adapter in the end of the VFL and then place the LC connector into the end of the adapter as shown here. Once the quality of the termination has been established, it is now time to finish the connector. Carefully slide the boot onto the connector to avoid damaging the fiber. The VFL can be used for troubleshooting. Notice the VFL window is glowing red, showing an open connection. When an issue has been detected with the connector using the VFL, it is possible to place the connector back into the tool and adjust the termination. Place the connector into the tool and slide the cover forward into the lock position. Slowly rotate the fiber roughly a quarter of a rotation. Place the tension loop back into place and open the tool to remove the connector. If it does not improve the condition, it can be re-terminated one additional time. Lastly, the tool should be free of dirt and debris and should be periodically checked for wear, specifically the termination fins present in the clear plastic cover, as this will affect the tool's ability to terminate the connector correctly.
Next up is our Lightspeed epoxy polish fiber connectors. Also as covered previously, these have a fair amount of craft sensitivity, so require a higher skill level by technicians, but do provide a good overall loss. So we have the video instructions for you, as well as the detailed step-by-step PDF instructions.
The Seaman Company fiber termination process uses a highly reliable acrylic adhesive and polish method featuring our Lightspeed brand activated cured adhesive, and has proven to produce superb repeatable results for long-term reliable performance. Seaman offers 3 standard connector styles for use with this method. The buffered termination process is identical for SC, ST, and LC style connectors. For clarity, the SC connector is the primary connector shown throughout this video using a 900 micron buffered fiber. Before beginning the termination, prepare a clean, dust-free work area and verify that all required tools are available. The Lightspeed tool kit plus the Lightspeed consumables kit will be required for proper termination of the SC, ST, or LC connector. If using the LC connector, you will also need the LC upgrade kit containing the LC polishing puck and the LC microscope head. The LC torch is also included for use with the jacketed style terminations not covered here. Note that the F-Term L2 toolkit includes empty dispensers for the water and the alcohol. Apart from the limited supply of alcohol-soaked pads provided in the consumables kit, both dispensers will require filling prior to termination. The alcohol dispenser is provided empty because of federal shipping restrictions. For best results, it is highly recommended that 99% reagent-grade isopropyl alcohol and distilled or deionized water be used. All connectors consist of several components: a strain relief boot sized for the 900 micron buffered fibers, the connector body, and the dust cap. The SC duplex connector, as shown here, also includes the outer housing and duplexing clip. Prepare the adhesive syringe by unthreading the cap and installing the metal syringe tip provided. The nose of the jacket stripper tool may be used to assist in unthreading difficult syringe caps. After exposing an adequate length of buffered strands from your cable, the first step is to install the strain relief boot. Perhaps one of the most commonly forgotten steps, this can certainly be frustrating if discovered after polishing several connectors to perfection. Slide the 900 micron boot onto the buffered strand, narrow end first until it is out of the way. Using the template card provided, choose the proper template for the connector being terminated. The LC template is on one side and the SC and ST on the opposite side of the card. Using the marker pen provided, measure and mark the buffer strip length from the end of the fiber as shown on the template. Using the buffer stripping tool, remove the measured section of buffer coating, including the protective undercoating. To avoid breaking the fiber, remove the buffer in at least 2 sections. Carefully inspect each fiber after stripping to be sure the protective coating was stripped off during this process. With some fiber types, under certain conditions, the clear protective coating may not strip off along with the buffer. Notice the partial protective coating remaining on this fiber after stripping. Sometimes mistaken to be the fiber cladding, this coating must be completely removed for the fibers to fit in the connector. After stripping, use a dry lint-free wipe to clean the fibers and remove any remaining remnants of the coating. Avoid touching or contaminating the fiber after it is cleaned. Prepare the primer bottle by inserting it into the stand provided and uncap. Always inspect the date shown on the label of both the adhesive and primer to be sure the product has not expired. When not in use, both the primer and adhesive should be capped and stored within the temperature range indicated. Dip the entire exposed length of fiber, including some portion of the buffer material, into the Lightspeed primer and place in a protected area. Be careful not to break the fiber by contacting the bottom of the primer bottle. Notice the minimum depth line marked on the label as reference point to prevent this from occurring. The buffered style termination is identical for the SC, ST, or LC connector styles. First, remove the dust cap from the connector and insert the adhesive syringe tip into the connector housing until it seats firmly inside. Inject the Lightspeed adhesive until a small dot of the adhesive appears at the ferrule tip. Also inject a small amount of adhesive into the back end of the connector. This ensures bonding of the buffer to the connector, strengthening the termination. Be careful not to overfill to prevent a backflow of adhesive. Next, insert the fiber into the connector until the buffer bottoms out inside the housing. Be sure the fiber is being inserted into the center of the connector and not the space between the inner and outer body. If the fiber seems to be catching within the inner body, it may help to rotate the connector during insertion to assist in guiding the fiber into the ferrule. Once the primer-coated fiber touches the adhesive, the curing process will start and fiber insertion will become noticeably more difficult if not fully inserted within 10 to 15 seconds. Allow at least 30 seconds cure time before proceeding. After the adhesive has cured, you are now ready to score the excess fiber using the scribe tool. First, inspect the blade to ensure it is clean and in good condition. The sapphire blade is double-edged and may be reversed if one side has been damaged. Hold the blade of the scribe tool flat against the ferrule tip with the beveled edge facing up. Carefully score the fiber on one side close to the intersection of the ferrule tip and fiber. Do not use excess pressure to prevent fiber breakage and uneven fractures. If the fiber stub breaks off during the scoring process, you may continue with the polishing process, but it is possible that the glass may have fractured down into the ferrule tip slightly. Inspection with the microscope after polishing will reveal this result. Be sure to keep track of your fiber pieces. They are difficult to see, and if these glass fibers are not properly disposed of, they may cause serious injury. Also remember to clean any adhesive off the blade of your scribe tool before it dries. If properly scored, the excess fiber can be removed with a straight, non-twisting pull. Deposit the fiber piece in a safe place, such as onto a piece of the electrical tape or into the debris container included. If the fiber does not readily pull off, repeat the previous step, scoring on opposite side of fiber. Prior to polishing, the boot may be slid into place to provide additional support during the subsequent polishing steps. Be careful sliding the boot into place. Some connector styles may be more difficult than others. Gently work the boot onto the back of the connector, being careful not to slip and break the buffered fiber where it enters the connector. Also be careful not to bump or brush the end face of the ferrule tip before polishing. The small fiber nub is still somewhat vulnerable to being fractured. Using the gray 12-micron film, perform an air polish. Gently brush the ferrule tip against the dull side of the polishing film in a figure 8 fashion to wear the small fiber protrusion into a smoother, more polishable tip. Continue until the tip is almost flush with the ferrule. The number of revolutions will vary dependent upon the length of the fiber stub left after cleaving. Prepare the polishing pad and puck by cleaning with an alcohol wipe to remove any debris that may adversely affect the polish. Position the pad onto a flat surface with the rubber side facing up. Place the pink 3-micron film onto the polishing pad with the glossy side of film down and remove any air that may be trapped between the pad and film. Add a minimum of 3 or 4 drops of distilled deionized water onto the section of film to be used. Carefully insert the connector ferrule into the appropriate polishing puck and gently place onto the pad. For LC connectors, use the puck provided with the LC upgrade kit. Avoid bumping the unpolished ferrule tip on the puck or crushing the tip down onto the pad. Gently grip the connector, apply medium pressure, and polish the tip in a 50 to 75 millimeter or 2 to 3 inch figure 8 pattern for 25 to 30 revolutions. For best results, avoid over-polishing or using excessive pressure. To optimize optical performance of the connectors while maximizing polishing film life of the pink and purple films, use separate sections of the film per 14 connectors. Using 5 sections of the film as shown here assures a life of at least 70 connectors per film. Variables such as amount of adhesive on tip, size of figure 8, and polishing pressure can also affect film life. Next, remove the connector from the polishing puck and clean the ferrule and puck to prevent particles from transferring onto the next film. It is also important to thoroughly clean the surface of film prior to storing to assure ideal conditions for the next connector. Allowing the film to dry without cleaning off the debris can adversely affect subsequent connectors. Now replace the pink film with the purple 1-micron film. Prepare as done with the pink film. Glossy side of film down, remove any trapped air, add several drops of water, and continue polishing with medium pressure again for 25 to 30 revolutions. Again, remove the connector from the polishing puck and clean the ferrule, puck, and surface of film. The final polish with the white finishing film is required for single mode and recommended for multi-mode 50-micron connectors that are going to be used for high bandwidth laser optimized applications. Replace the purple film with the white finishing film and prepare as done previously with several drops of water. The finishing film differs from other films in that each section of this film can only be used one time. Choose an unused section of this film and continue polishing, but use light pressure for 25 to 35 cycles. Also limit the size of the figure 8s to 1.5 inches in height. To optimize optical performance of the connectors while maximizing polishing film life of the white finishing film, use a separate section of film for each connector. Dividing the film into 16 quadrants will assure maximum film life. Prior to inspecting the connector with a microscope, clean with an alcohol wipe followed by a dry lint-free wipe. Prepare the microscope with the universal head for SC and ST connectors, or the LC head for the LC connector. The microscope is 400 power, and unlike the typical 100 power microscopes, will provide a detailed view of the resultant polish. This level of magnification is very helpful in identifying a poorly polished connector, which is required to ensure optimum insertion loss and return loss performance. For proper use of the microscope, reference the instructions included with the scope. Fully insert the ferrule into the microscope, depress the button to illuminate the end face, and inspect the fiber to ensure there are no scratches, voids, or chips. If the polish is acceptable, place the dust cap on the connector until your network connection is ready to be established. If any portion of the fiber has fractured down below the ferrule surface, it will appear as a dark region through the microscope. If the fracture is not too far below the ferrule surface, a recovery polish can be used to polish down the ferrule surface and fiber flush with each other. This procedure requires the bronze-colored 6-micron recovery film, part number FT-PF6. This film is sold separately and not included in the consumables kit. Using the 6-micron recovery film, perform a pad polish step identical to the initial one, then continue as normal starting with the pink 3-micron film. Be sure to clean between steps to prevent transfer of debris between films. For larger jobs, consider purchasing additional polishing pads and pucks to minimize setup and cleaning time. SC duplex connectors will require one additional step, the housing and duplexing clip assembly. Insert the connector body into the housing by orienting the chamfered corners of the connector relative to the key on the housing as shown here. Grasp the boot and push firmly. The connector should snap into the housing. Join two simplex SC housings to create a duplex connector by snapping together with a black duplex clip. Use the A and B designation markings on the duplexing clip to identify proper polarity. SC duplex connectors can be uncoupled by simply squeezing the front of the duplex assembly together or with a small screwdriver inserted as shown.
And finally, we have the OptiFuse Fusion Splice fiber connectors. So if you own a fusion splicing machine, this may be a preferred method for termination for you. We have video instructions for this as well as we have the PDF instructions with the step-by-steps.
So with that, we've wrapped up Module 5 of Siemens Online Registered Installer Program. Next up, Module 6, Installation and Administration.